Hello and welcome to Modeling a Continuously Stirred Tank Reactor by Matthew Anderbrahan and Adnan Aziz. Getting straight into our executive summary, spectrophotometry was used to measure changes in absorbance over time in our ideal CSTR, enabling us to determine ideal steady-state operating conditions. The comparison of experimental and theoretical results highlighted key deviations and provided insights into the discrepancies. The CSTR mole balance was used to calculate steady-state conditions, ensuring the accumulation term to be zero. Lastly, primary sources of error were discussed and the effects on the results. Next, getting into a brief background behind the CSTR and our reaction, we made some ideal CSTR conditions and assumptions, as shown with the formula on the left. First, we assumed perfect/uniform mixing, also operation taking place at steady state, meaning the volumetric flow rate in and the volumetric flow rate out were equal. The space-time relationship is volume over volumetric flow rate, and we discovered that steady state is achieved in 3 to 5 space-times. Next, a little bit about our reaction. It's the bleaching reaction of bromophenol blue in a CSTR, and we discovered the rate law as shown here in our previous lab with a kinetic constant of 34.9. The recommended reaction parameters as per the lab manual were a volume of 200 to 800 milliliters, a dye conversion of 30 to 50%, and an operation time of 30 plus minus 5 minutes. Getting into our methodology, we had a few things to determine before our first trial. First, finding the flow rate using the values from lab 1, such as the K value, as well as a conversion that we determined to be 30%. Next, we had to calculate the inflow concentrations of both bleach and dye, then calculate the volume of bleach and dye needed to achieve these calculated concentrations, as shown with the 3 calculations on the right. First, the bleach concentration in the inflow was equal to 0.0027 molarity, with the reactor concentration being 0.00135 molarity, meaning 1 milliliter of bleach was added to our Erlenmeyer flask and half a milliliter being added to our CSTR. Next, for dye, we found an inflow concentration of 20 micromoles and a reactor concentration of 10 micromoles, resulting in 14 milliliters of dye being added to our Erlenmeyer flask, with 7 milliliters being added to our CSTR. Lastly, we calculated a volumetric flow rate of 38.39 milliliters per minute, which the pumps had to be set to a speed of 47 to achieve 19 milliliters per minute on each pump. 1/8-inch piping and pumps were used to achieve this. As for our CSTR reactor volume, we chose a volume of 350 milliliters with an outlet drilled at the 100 milliliter mark and an outlet pipe set at 350 milliliters to ensure steady state. We opted for this because a lower reactor volume allowed for a shorter space-time and achieving a greater steady-state percentage. Next, we chose to have 5 successful trials because we wanted to maximize the number of trials in the allotted time to ensure the accuracy of data and the reproducibility of steady state. As for measurements, the Genesis 30 spectrophotometer was used at a wavelength set to 591, and absorbance values were taken every 3 minutes for 30 minutes. As for our experimental process, the steps followed as are shown here. First, we had to set up all required equipment, including zeroing the spectrophotometer, calibrating pump flows, setting the CSTR to steady state, and measuring out all calculated concentrations. Next, we collected samples from the outlet every 3 minutes in the cuvette and inserted into the spectrophotometer, recording all absorbance values. We repeated this for about 30 minutes or until steady state was achieved.
Thank you, Matthew. Now I'll be going over the results section for our lab experiment. So quickly want to go over trial 0. Trial 0 had different operating parameters from what Matthew just explained to us. We were able to learn from trial 0, revise our parameters, and get the 5 successful trials. But as you can see, for trial 0, we achieved a conversion of 71.2%. This is way out of range of the 30 to 50%. That's why it was deemed unsuccessful. And using the conversion of 71.2%, we found a K value of 64.9, 1 over molar minute. This is, again, very high and not the 34.9 used from lab 1. So we made some incorrect assumptions. Our space-time was too high. We doubled the concentrations in the reactor, which led to a higher conversion. Now, using the parameters Matthew just explained to us, we were able to find a space-time of 9.21 minutes. Using the first order steady-state CSTR material balance, we were able to find that when time is equal to 30 minutes and our space-time is 9.21 minutes, the system is at 96.15% of steady state. Now, this is exactly not 100%, but this is where we start to see deviations between our expected conversion and our measured conversion. Now, looking at our 5 successful trials 1, 2, 3, 4, and 5, in figure 2 and 3 of the absorbance versus time plots, we can see our conversions range from 38% to 35%, with an average of all 5 trials being 36.88%. Using that average, we were able to back calculate and find a K value for the reaction to be 23.8 1 over molar minute. Again, this is not the 34.9 1 over molar minute that we used from lab 1 in our CSTR mole balance, but this is where we start to see the deviation occur. Now, to make sure we actually met steady state in our reactor, we plotted a conversion versus time plot for all 5 trials. We found the equation and the derivative was found. Setting the derivative to 0, we were able to solve for x, which was 24.58 minutes. This is exactly where our line plateaued and steady state was met. At this x value, we were able to find conversion, which was 35% plus or minus 2%. Now again, this is just an approximation, as if we were to increase our time to 35 and 40 minutes, take more absorbance values, our steady state or x value would also increase. But this again is just an approximation, as a second order polynomial does not fully represent our data set, as the r-squared value is only 0.97. Now, we expected a 30% conversion from the CSTR mole balance, but we measured a 36.88% from an average of all 5 trials. Now, why did the deviation occur? Well, the CSTR mole balance assumes perfect mixing, constant temperature, and an adiabatic system. In this ideal condition, every drop of fluid that would enter the reactor is assumed to have identical composition, temperature, and no change in heat within the system. In our lab experiment, this is not what occurred. There were temperature fluctuations, inconsistencies in mixing, which all led to our results being different. Secondly, an assumed value of 1 was used for beta. Beta is the respect in order to bleach. This was found to be 1.25 from lab 1, but we assumed a value of 1 in our CSTR mole balance. We underestimated the reaction's dependency on the bleach concentration, which affected our results again. Also, using the accurate K value in the CSTR mole balance would also lead to accurate results. Now finally, the space-time only permitted 96.15% steady state achievement. This is an issue because the CSTR mole balance assumes 100% steady state and does not take into account transient operation. This also affected our results. Now, there were some sources of error in our lab experiment, especially the pumps. The pumps were very fluctuating, which affected our flow rates, especially when small gas bubbles enter the pipes. This affected the flow rates. The flow rate of 38.39 milliliters per minute was rounded down to 38 milliliters per minute, since measuring out 0.39 milliliters is highly difficult. And minor fluctuations in volume and small increases over 350 milliliters affected our steady state. To conclude, we found our key parameters and measured values, the most important being conversion of 36.88% for an average of 5 trials. And in the future, we recommend to get better results using the proper beta value calculated in the previous lab. Trying to achieve a lower space-time would also help, ensuring no contamination of bleach in the pipettes used, running trials for longer than 30 minutes, and also the proper use of the rate constant K in the CSTR mole balance. Thank you for listening.